Let us consider interference experiment, Young's double slit experiment. It is very important for the NEET and JEE. Most of the questions from wave optics will be asked from this experiment only. If they are asking some 10 questions, definitely 7 to 8 questions must be from the Young's double slit experiment, not in single exam. Okay, if you take average of 10 years, if you take 7 to 8 times, they will ask from the interference experiment, that is Young's double slit experiment. Okay, so let us have the experiment. In short, I can keep this as YDSE. Okay, Young's double slit experiment, right? In this, what are the necessary things? Already I discussed it, like there should be two waves, they must be coherent, and those two coherent must be superposing on each other. That we are going to discuss here. So consider a screen. Of course, here we are considering vertical slits. I'll tell you what is vertical slit and what is horizontal slit, but let us consider here what is, like in case of vertical slits it is. Okay, so this is a main line. So here is a source placed. The source sends the waves in all possible directions, that you know, and have a convex lens, right? So definitely convex lens, if the object is at this focus, the beam will be parallel to the principal axis, that you know from ray optics. So these are the two slits I am having, and identical slits I am taking. Identical slits meaning the slit width is same, that is A. Okay, slit width is generally W or A, they will consider W or A, doesn't matter. So two slits are having same width. Okay, either W or A. Yeah. So definitely here is a parallel beam. Okay, parallel beam meaning the wavefront is a plane wavefront. Okay, that is, this is the wavefront. Okay, wavefront 1, 2, 3. How many such wavefronts are possible? Infinitely many. It depends on your patience. Okay, so these are the wavefronts which are plane. So from the Huygens principle, every particle on the wavefront behaves as a secondary source. Okay, so this is the S1 you consider, and this is S2. Then S1 and S2 are also behaving as a sources. I mean, these S1 and S2 also sends the light waves in the right direction, I mean the direction of the incident wave. Okay, so from here the light wave will go, it will be travel like this. Yeah, so this pattern will be there. I will not draw the total pattern here because we are interested in location of the fringes here. Okay, so this wave may go, and this is a screen over here placed. The distance from the slits and the screen is capital D. Okay, and the distance between the two slits is generally small d. Okay, so from S1 to this point P, the wave Y1 will go and meet there, and from S2 to the same point P, the wave Y2 may go and hit. Okay, you should use a scale for this actually to have to come this straight line. So definitely this is Y2. So Y1 and Y2 are superposed on each other, and these two waves are coherent waves. Okay, why they are coherent? Because S1 and S2 are coherent sources. Why they are coherent sources? Because S1 and S2 are on the single wavefront. Okay, on a single wavefront, all the particles should oscillate with the same amplitude and with the same phase, right? So thereby these S1 and S2 are satisfying the criteria of coherent waves. So only S1 S2 are called as coherent waves. Without S1 S2 slits, we can't have the interference pattern. Okay, so the purpose of S1 and S2, the slits purpose is to make the waves as coherent. Otherwise interference phenomena is not possible without slits. Okay, so only on my whiteboard the light is not having any interference pattern here. Dark fringe, bright fringe, dark fringe, bright fringe are not found here, because the light is incidenting on the board is not coherent light here. Okay, if I had used any two slits in front of this board, then you may see here the white and dark, like bright and dark fringes here, okay? And you are not seeing the bright and dark fringes because there is no slits, okay? So here the slit purpose is to make the waves as coherent waves, okay? So let us consider next thing. So they are forming here. What is the intensity at this point P? Generally, the intensity of coherent waves, intensity distribution formula just now I discussed, it is going to be I1 plus I2 plus 2 root I1 I2 cos pi. And if you consider I1 I2 are equals to same, that is I0, because the slit widths are same, okay? Slit width is same. If width of the slit is same, then amplitude of the each wave also same. If amplitude is same, then intensity will be same. Remember, if slit width is equal, then amplitude of y1 and y2 equal. If amplitudes are equal, then intensities I1 and I2 are also equal. Let the intensity be I0. Then if I substitute there, I will get a formula that I equals to 4 I0 cos square 5 pi by 2. How I am getting this? It's a matter of waves chapter, right? So if you want to see how we got this, just substitute there and take that 1 plus cos pi equals to 1 plus cos pi formula will be 2 cos square pi by 2, okay? If you substitute in this, you'll get it, okay? You can try that, right? But the thing is whether this P is having bright fringe or dark fringe. Whether at P intensity is maximum or minimum, or neither maximum nor minimum. How much the intensity at P, that is decided by the phase difference. See, it is very clear if phase difference is 90 degrees, sorry, not 90, phase difference is 180 degrees, 180 by 2 is 90, cos 90 value 0. So intensity becomes 0. If intensity is 0, then it is going to be dark fringe. The corresponding interference is going to be destructive interference. Understand? So if phase difference is 0, for example, then cos 0 is how much? 1. Then intensity will become maximum. So depending on the phase difference, there will be intensity, okay? But phase difference depends on what factor? Again, the first statement is depending on the phase difference, the intensity will be there. But phase difference depends on what factor? Remember, phase difference depends on the path difference, okay? Del x. What is del x here? Path difference. What is path difference? It is very simple. The path difference is nothing but the path length, the difference of the path length traveled by two waves. See, the second wave is traveling from S2 to P. The path length traveled by the second wave is S2P. And the first wave is traveling from S1 to P. The path length traveled is S1P. The difference in their paths, which path? It is not the geometrical path, please remember, it is the optical path, okay? Optical path is never, it is generally not equals to geometrical path. It is always greater than the geometrical path, okay? Optical path length is equals to refractive index into actual path length. Actual path length is say L, remember, okay? For optically denser medium, optical path length will be greater than the actual path length. So here S2P minus S1P is a difference in the optical path length, okay? If the difference in optical path length is called as path difference, okay? Depending on the path difference, phase difference will be there. Depending on the phase difference, intensity will be there. So it's very clear if I generalize the statements here. Depending on the position of the particle, position of the point where you are considering. For example, here you consider, say the point is Q. Then from S1 to Q and S2 to Q, the path difference will be same. Will be different, okay? If you consider this, okay? So here obviously S1 to Q is larger than the S2 to Q. So for Y1 has to travel more path length than the Y2. So definitely at Q intensity will be different again, not equals to P. Understand? So my statement you should remember, depending on the location of the particle, there will be path difference. Depending on the path difference, there will be phase difference. Depending on phase difference, there will be intensity. Okay, so what is deciding actually, path difference only deciding the intensity. Okay, so we should learn in terms of path difference, and that is what I am going to give you. Okay, so it's very simple statement. If you remember, I will make the statement here. Okay, let it be del x, right? I'll give the equation for del x also, but now I am giving a statement that you should remember. It's very simple. If the path difference is, please remember the statement, if the path difference is even multiples of the lambda by 2, if the path difference is even multiples of the lambda by 2, then it is going to be constructive interference. Okay, if the path difference is odd multiples of lambda by 2, then it is going to be destructive interference. Corresponding fringe is dark fringe. That means here I can have two cases. If it is integer multiples of the lambda by 2, okay, some books they will write even multiples of 2n is always even, right? 2n even multiples of the lambda by 2, then it is constructive interference. Corresponding fringe is bright fringe. Okay, odd multiples of the lambda by 2, if it is odd multiples of the lambda by 2, then it is going to be dark fringe. Okay, it is a destructive interference. Okay, so this thing, many books they will write integral multiple of lambda. That is also correct. Okay, because 2 will get cancelled, n lambda, n is running from 0, 1, 2, 3 and so on. Here n is running from 1, 2, 3 and so on. Okay, just now I have told you that we have discussed that is a dark fringe and bright fringe conditions. That is for bright fringe n equals to n lambda capital D by small d. For dark fringe it is 2n minus 1 into lambda capital D by 2d. Say n equals to 0, then it is going to be at the mean position. N equals to 1 lambda capital D by d. This is going to be lambda capital D by 2d. Okay, this is a first bright fringe, this is a first dark fringe. N equals to 2, it is 2 lambda capital D by small d, and here it is 3 lambda capital D by 2d. This is second bright fringe, this is second dark fringe. Similarly, third bright fringe, third dark fringe, and so on you can have. If you draw the situation on the board, so if you consider this is a main line, okay, so central bright fringe, this one, if you consider this is a bright fringe, okay, then immediately after bright fringe, dark fringe should form. Okay, this is a dark fringe, and below also there should be a dark fringe. Okay, then after the dark fringe, bright fringe should form. Okay, similarly it will go on, like this is bright, bright, bright. Okay, and this is going to be dark, dark. You have to fill this. Okay, so let us sweep up this otherwise. Yeah, this is bright. So this is n equals to 0, this is n equals to 1, this is also n equals to 1, but this is above, below. Here this is n equals to 1, of course, but this is a dark fringe, first dark fringe, and this is a n equals to 1, first dark fringe, above and below. Okay, remember, above the line there will be n fringes, below the line also there will be same number of fringes. Okay, we will discuss that again. So the diagram is like this. Actually, when the slits are circular, these fringes will be hyperbolic. That I will show in the next board. Okay, this is how they will form actually. First central bright fringe, then dark fringe, and then bright fringe, like that it will go. Increase. Okay, so this is what actually beta. This is, we call it as fringe width. fringe width. Okay, now there is something called angular fringe width also. The questions can be asked from the angular fringe width. Okay, angular fringe width, symbol is theta. This we can write the d sine theta equals to n lambda for bright fringe we can take, and sine theta equals to lambda by d regardless of the order of the fringe. If I consider n equals to 1, then sine theta equals to lambda by d. For small angles, the sine theta we can approximately take it as theta. So we can rewrite this theta equals to lambda by d. This theta is called as angular fringe width, which is directly proportional to wavelength of the light and inversely proportional to gap between the two slits. Okay, so based on this, there is a problem in the NEET exam. Okay, so I'll tell you the problem based on this. Okay, and they said with a wavelength lambda 1 5890 angstroms, the angular fringe width is observed to be 0.20 degrees. Okay, it is angle, so it may be in degrees or radians. Okay, so for this wavelength the angular fringe width is 0.20, and the question they asked is, if final second time the angular fringe width is 10% larger than the first angular fringe width. That means what? For a new wavelength, the angular fringe width is 10% larger than the previous angular fringe width. Okay, that means theta 2 equals to 1.1 times the theta 1. Okay, then what is the final, that second wavelength? This is a question actually. Okay, so I am not giving the total question here, description I am not giving. They given lambda 1 theta 1 and also theta 2 they mentioned, and they are asking us to find the lambda 2 for a fixed small d distance. Okay, it is very simple to answer. Since theta proportional to lambda for a constant small d, we can say fractional change in the theta equals to fractional change in the wavelength, right? So we can write from here fractional change in theta by that is fractional change in theta is 10%, so 1 by 10 equals to fractional change in the wavelength we need to find. Okay, so it is very simple. Del lambda by initial lambda equals to 1 by 10, then del lambda equals to lambda 1 divided by 10. Lambda 1 is how much? 5890 angstroms. So change in the wavelength equals to 589 angstroms. Then final wavelength is lambda 2 equals to lambda 1 plus change in the wavelength. So if you add 5890 with the 589, you will get some number that is in angstroms. This is the answer. Okay, so based on the angular fringe width formula there was a question, and of course one more question also there. So generally in NEET exam wave optics chapter, high priority is given for the Young's double slit experiment only. The question may not be from polarization and also diffraction, but it definitely come from the Young's double slit experiment. If you see the previous year question papers, you will find many questions from the Young's double slit experiments than diffraction and polarization. Okay, so we can consider the Young's double slit experiment is an important topic in the wave optics chapter. Okay, so I hope you understand this. This is angular fringe width. Okay, angular fringe width formula is lambda by small d. As lambda increased, small theta increases. As small d decreased, theta will increase. Okay, and one more thing that we can realize here, the theta is independent of the order of fringe. Okay, whichever the fringe you are taking, like nth bright fringe or nth dark fringe, it will have the same angular fringe width. Okay, and it depends only on the wavelength and also small d. Let us see how many number of fringes are formed in the interference pattern. How many number of fringes are formed, like bright fringes are how many, dark fringes are how many, total number of fringes also we will discuss. Okay, for that again we should use the d sine theta equals to n lambda for bright fringes. Okay, so where n is a order of the fringe, n may be 1, 2, 3 and so on, the last fringe. Okay, So we can consider this sin theta equals to n lambda by small d, right? But mathematically we know sin theta is less than or equals to 1. If theta is maximum, that is 90 degrees, then sin theta will be equals to 1. So for maximum value of sin theta equals to 1. So n into lambda by d, the maximum value will be equals to 1. I hope you got it, right? Sin theta equal to this value n lambda by small d, right? But sin theta maximum value is 1. So n lambda by small d values, n lambda by small d maximum value also equals to 1. So we can find n equals to d by lambda. Okay. So what is this n here? That maximum, the nth bright fringe we can say. Okay. That means if you consider this is a reference level, okay, like n equals to 0 in the interference pattern. Okay, this is n equals to 1, n equals to 2, 3, 4 and so on will be there 1, 2, 3, 4 and so on n bright fringes, and below also there will be 1, 2, 3 and so on, there will be n. So total number of bright fringes, if you are finding, the total number of bright fringes equals to above these many, below also these many. So 2 times d by lambda plus the n equals to 0 is one more bright fringe. I hope you got it. Above the line there are d by small d by lambda number of bright fringes. Below the line also d by lambda number of bright fringes. Okay. So total 2d by lambda, but you have to include the central bright fringe also. Central bright fringe is one more, so you have to equate. I mean, you have to sum. You have to add that one. Okay. So I hope you got it. This is the number of bright fringes formed, right? Similarly, if they are asking you to find the number of the dark fringes, okay, the dark fringes if you find, for the dark fringe this d sin theta should be equals to, you know already, 2n minus 1 into lambda by 2, odd multiple of the half of wavelength, that is a path difference. Okay, and from here I can rewrite sin theta equals to 2n minus 1 into lambda by 2d, and again sin theta is always less than or equals to 1. The maximum value of sin theta is equals to 1, that you know. We can equate for this again and we can find the number of minima. Okay, the number of minima will also be equals to 2 times d by lambda plus 1. Okay, if you prove this, if you follow, I mean if you further proceed, and you will find the same thing. So what did you understand here? The number of maxima, number of minima are equal. Okay, I hope you got it. And this is the number of minima and maxima. That means above the reference line number of maxima, below the reference line number of maxima are equal. Okay, including the central maxima, these many maxima will be there and these many number of minima will be there. Okay, and you know maxima stands for bright fringe, minima stands for dark. Let us see the missing wavelength. Okay, this is one more thing. Okay, the missing wavelengths. Remember, the missing wavelengths are corresponding to the dark fringes. Okay, missing wavelengths are corresponding to the dark fringes, right? The missing wavelength general formula equals to d square by 2n minus 1 into capital D, where n runs from 1, 2, 3 and so on. Proof I am not giving here. Proof is not required here, of course, right? Because we have to equate the path difference equals to, you know, 2n minus 1 into lambda by 2 again, and we have to follow the same way. You will get this equation, but I can tell you the meaning of this. If you take n equals to 1, then d square by capital D, missed wavelength, n equals to 2, d square by 3d, next d square by 5d and so on. These wavelengths are missed in that. Okay, if it is a polychromatic light, I mean there are number of wavelengths. Okay, generally monochromatic light will be there and also polychromatic. Monochromatic means only one wavelength. Okay, polychromatic means there are many wavelengths, like white light. White light is a polychromatic. In that polychromatic light we will have the missing wavelengths. Okay, so in general, Young's double slit experiment, they will ask you the question based on the topic. they will use two different wavelengths not simultaneously, one after the other. For example, lambda 1 they have used and the total number of fringes are n1, and next lambda 2 wavelength they will use, the total number of wavelengths will be total number of fringes formed is n2. The relation between lambda 1 and lambda 2, n1 and n2 is very simple. The relation is very simple, is going to be n1 lambda 1 equals to n2 lambda 2. Okay, we will consider an example based on this, right? So let us consider a problem. Suppose a wavelength of 6000 angstroms is used and there are 10 fringes are formed. Okay, suppose there are 10 fringes are formed in the field of view. Okay, now second time they are using 8000 angstroms wavelength. How many number of fringes are observed in the interference pattern? This is the question actually. It's very easy and it is up to NEET level problem. Okay, and sometimes JEE mains level also they can ask. Okay, because the nowadays paper is coming very easy. Okay, so we can equate in this formula, that is n1 lambda 1 equals to n2 lambda 2. Actually this is coming from the formula n1 beta 1 equals to n2 beta 2. Okay, this is actually derived from n1 beta 1 equals to n2 beta 2, because n into beta is a constant for any interference pattern, where n is the total number of fringes formed, where beta is the fringe width. Okay, n into beta is the width of the screen we can have, or field of view we can have. Okay, so that length the length of the field of view is constant, no? So only n into beta is constant. So n1 beta 1 equals to n2 beta 2, provided the capital D remain constant. What is that constant? Capital D remain constant, right? And of course small d. So if we substitute in this formula, then you will get n1 lambda 1 equals to n2 lambda 2. That is 10 into 6000 angstroms equals to n2 into 8000 angstroms. Very simple. Angstroms will be thousands cancel. Then n2 equals to 60 by 8. 60 by 8 will be approximately 7.5. So what we have to take actually 7.5, 756, yeah, of course 7.5. 7.5 means the integral value of 7.5 you should consider 7 fringes. Okay, so bracket of 7.5, that you know how to take mathematically, very simple. So this is one more case they can ask, that is n1 lambda 1 equals to n2 lambda 2. In the same case, like same way, where they are using two wavelengths. Okay, they will ask you based on the situation where the fringes are coinciding. For example, if I use this as a reference line and this is a screen with the lambda 1 wavelength, say this is a point where n1 bright fringe is formed. Okay, with the lambda 2 wavelength, at the same point there will be n2 bright fringe formed. Okay, that means what? The n1 bright fringe of the lambda 1 wavelength is coinciding with the n2th bright fringe of the lambda 2 wavelength. Did you understand? So if in that situation, how to solve that? Here there are three cases. Here there are we can have three cases. Okay, that is first wavelength bright fringe is coinciding with the second wavelength bright fringe. First wavelength dark fringe is coinciding with the second wavelength bright fringe. Okay, similarly first wavelength bright fringe is coinciding with the second wavelength dark fringe. Okay, and remaining four one case also we can have, like lambda 1 lambda 2, right? So bright fringe of the first one may be coinciding with the bright fringe of the second one. Bright fringe of the first one may be coinciding with the dark fringe of the second one. Okay, dark fringe of the first one may coincide with the bright fringe of the second. Dark fringe of the first one may coincide with the dark fringe of the second. Are you understanding that? So there are four cases actually. Okay, so we are going to discuss this elaborately. I mean, nth bright fringe of the lambda 1 is coinciding with the mth bright fringe of the lambda 2. Similarly, nth bright fringe of the lambda 1 is coinciding with the mth dark fringe of the lambda 2. Okay, so there are many. Suppose nth bright fringe mth bright fringe. Okay. So let me explain here with the diagram. From here, say this is the slits, here slit 1, slit 2. This is a point where the fringes are forming. Okay. So with the lambda 1 nth bright fringe, same location with the another wavelength lambda 2 mth bright fringe. Okay. That means from here to here the distance is same, this gap is same, but the order of fringe is different because the wavelength is different. You can simply say that the nth bright fringe of the wavelength 1 will be n into lambda 1 into capital D by small d. This is actually y when the lambda 1 is used. Mth bright fringe of the second wavelength, that is going to be m into lambda 2 into capital D by small d. Okay, and this is also equals to y, so we can equate. Then you will get lambda by d is, sorry, capital D by small d is cancelled. Then you will get n lambda 1 equals to m lambda 2. Similar formula what we have used previously. Okay, this is when nth bright fringe is coinciding with the mth bright fringe of lambda 2. Okay. Next case, nth bright fringe of lambda 1 coinciding with mth dark fringe of the lambda 2. Okay. So case 2, this is case 1, case 2, nth bright fringe with mth dark fringe. So in this case what happens, this distance is the nth bright fringe distance for the lambda 1. So n into lambda 1 into capital D by small d is this one when lambda 1 is used. But when lambda 2 is used, it is 2m minus 1 into lambda 2 capital D by 2d. This is the dark fringe common formula that we have discussed. Okay. So instead of n, we have to use m here because they mentioned as m. But they both must be equal because they are forming at the same point. If you equate, then it cancels here. Then n lambda 1 equals to 2m minus 1 into lambda 2 by 2, or 2n lambda 1 equals to 2m minus 1 into lambda 2. This is the case when nth bright fringe is coinciding with the mth dark fringe. Okay, this is case 2. I hope you got it. And moving to next third case, it is case 3. Now, like nth dark fringe of the wavelength 1 is coinciding with mth bright fringe. Then first case, it is a dark fringe, right? So 2n minus 1 into lambda 1 capital D by 2d. This is the nth dark fringe of lambda 1. Mth bright fringe, that is m lambda 2 capital D by small d. Both are equal again. If you equate and cancel this, you will get 2n minus 1 into lambda 1 equals to m into lambda, so 2m into lambda 2. This 2 will come over here, right? So now you can guess the fourth case. What is the fourth case? Nth dark fringe is coinciding with the mth dark fringe. Okay, in that case it's very simple to answer. Okay, let me whip up this. So case 4, that mth dark fringe with mth dark fringe. Nth dark fringe of lambda 1 is 2n minus 1 into lambda 1 capital D by 2d. And mth dark fringe of the lambda 2, it is 2m minus 1 into lambda 2 capital D by 2d, both are equal. If you cancel, you will get 2n minus 1 equals to 2m minus 1. This is a case. You should remember these 4 cases, and the problem can be asked any one of these 4. Okay, I hope you all got it. Let us consider the Young's double slit experiment in a medium. Till now what we have discussed is actually the experiment is done in air. Okay, so if it is done in water or any other medium where the refractive index is not equals to 1, there is some value of mu they will give you. So we will consider that is Ydse in a medium. Right, so there will not be big difference actually. Okay, the phenomena, everything will be same, but what will change, the wavelength will change, right? Once the wavelength is changed, then everything, every equation where the wavelength is involved will be changed. Okay, how the wavelength will change, suppose in air the wavelength of light is lambda, in medium the wavelength of light is lambda prime, for example, and the medium refractive index, air refractive index is 1, medium refractive index is mu, then the lambda prime equals to lambda divided by mu, that you know very well. If optically denser medium is there, it will have less wavelength, less speed. So it is a medium which is optically denser, so it will have less wavelength than in air. So what will change here? First thing is the location of nth bright fringe and nth dark fringe formula, what we have discussed. Yn is n lambda capital D by small d. Okay, and for dark fringe it is going to be yn equals to 2n minus 1 into lambda capital D by 2d. Okay, these will change. Yn prime equals to n lambda capital D by mu d, because wherever lambda is there you have to take lambda by mu. So yn prime dark fringe equals to 2n minus 1 into lambda capital D by 2 times mu d. Okay, so this is in air, this is in medium. In air, what is the beta formula? Lambda capital D by small d is the fringe width. What is the theta formula? Lambda by small d, angular fringe width. Similarly, in medium, these two will be varied. The beta prime equals to lambda capital D by mu d. It will decrease. It will become less width. Okay, in air, if this is the width, then in medium it will become thinner. Okay, so theta prime, that is angular fringe width in the medium, is going to be lambda by mu d. Okay, similarly the number of fringes formed we have discussed already. The number of fringes formed, n maximum equals to, or simply both are equal, right, what we have showed already. So n equals to formula 2 times d by lambda plus 1 in air. Okay, but this will come n prime equals to, in medium it is 2 mu d by lambda plus 1. Why this mu came in the numerator? Because lambda, you have to take lambda by mu, the mu will go up. Okay, let us see the displacement of the interference pattern. What is displacement of interference pattern? Actually, when we introduce a thin film which is having some refractive index of mu and thickness small t in between S1 to P or S2 to P, right, and there will be shift in the interference pattern, either it will be shifted above the line or below the line, that we are going to discuss here. So for that I have to draw the diagram. The concept name is very simple: displacement of interference pattern, simply pattern. So interference pattern is observed on the screen, right? Okay, and that pattern will be shifted. Why it is shifting, that we are going to discuss with the diagram. Say this is the slits here they have given. Say this is S1 with width, okay, and the same distance here, S2, and here is a screen. The distance between the slits and screen, as usual, it is capital D, and the distance between the two slits is also small d. Then S1 to P, there is a ray which will go somewhere here, the P. S2 to P also one ray will come and join, okay. Sorry. Okay, approximately it should be a straight line. We are introducing a film. Okay, this has some refractive index mu and thickness small t. Remember, I already told in case of double slit experiment, right? The previous class, okay. I already told that whenever there is a medium here, okay, the optical path length will be different, okay. Due to this medium, due to this film, there will be shift. The shift is going to be mu minus 1 into thickness. How it is coming, that is discussed in the ray optics, okay. This is a shift actually, okay. Optical path length shift, it is this much. Now effective optical path length, I mean effective distance from S2 to P, S2 to P is going to be S2P plus, I mean geometrical length plus this one, u minus 1 into T. I hope you got it. Actually, in geometry, the distance between S2 to P is simple. From here to here, how much distance is there? That is the distance, okay. But whenever there is a light following, I mean propagating through this medium, it will experience this shift, right? That is the shift is nothing but the difference between optical path and actual path. I told you already, optical path is mu times the actual path. Actual path is thickness, this is T, okay. So optical path is mu T. Mu T minus T will be mu minus 1 into T. So this is the shift. This is the extra distance that is light has traveled, okay. Actually in space only distance from S to P is fixed, but when you introduce a film like this, for light it is some extra distance. That extra distance is mu minus 1 into T. So that extra distance should be added to the actual distance, okay, S2P plus mu minus 1 into T, okay. Now the new path difference equals to the new S2P plus mu minus 1 into T minus S1P. Actually when this was not there, what we have taken, you did not consider this, okay, only S2P minus S1P, okay, because it was not there in that case. But now we are introducing this. Because of this, there is some extra distance that light has to follow, okay. So only this is included. I hope you got it. And this del x prime, we can say S2P minus S1P plus mu minus 1 into T, right. This is going to be d sine theta prime plus mu minus 1 into T. This is the del x prime, okay. So let us consider this diagram over here. This is theta prime, okay, and taking the sine theta as tan theta again, the tan theta prime plus mu minus 1 into T. Tan theta prime means this distance, say yn prime. What is that? Nth bright fringe or dark fringe? Nth fringe location is yn prime. So we can say d into yn prime by capital D, because tan theta is opposite by adjacent, okay, plus mu minus 1 into thickness. This is the path difference when we introduce this one over here. So what is happening to the remaining quantities? Let us discuss, okay. Let me whip out this. So as we know already, that is, if path difference is even multiples of lambda by 2 is a bright fringe, odd multiples of lambda by 2 it is a dark fringe, okay. So similarly, if this path difference is even multiples of lambda by 2, is going to be bright fringe. Odd multiples of lambda by 2, it's a dark fringe. Okay, so we are going to discuss that. So del x prime, we can have two cases here. Even multiples of lambda by 2, that is bright fringe. Let us equate this. Okay, so d yn prime by capital D plus mu minus 1 into t equals to n lambda, I can say. Then I can equate for yn prime. If I equate, yn prime equals to, it will come n lambda capital D by small d minus mu minus 1 into thickness into capital D by small d. Okay, so what did you notice here? The nth fringe, nth bright fringe with the film, this is with the film equals to, this is actually nth bright fringe without film, right? We have already seen. Okay, nth bright fringe without film minus this one, that is mu minus 1 into dt by small d. That means what? Where the first bright fringe was formed, right? For suppose central bright fringe, if you consider, central bright fringe will be on the central line. Okay, if you consider the experiment this way, over here the central line. Okay, but because of this film, okay, because of this mu or because of this thickness t, right, there is some shift. That shift is actually a minus. Minus means it is coming downward, we can say. I'll tell you when it is come down and when it is go up. Okay, after the completion of everything, very simple. But I can say this, we can conclude it as a displacement. Okay, displacement means not only the central bright fringe shifts. Okay, first bright fringe, second bright fringe, third bright fringe, every fringe will be shifted by these many meters. Okay, either downward or upward. Okay, let me tell you the shortcut here itself. Okay, the shift will be, or displacement will be, in a direction in which the film is introduced. For example, S2 to P, in between S2 and P the film is introduced, then it will come downward. Okay, because we consider S2 is downward, below the line. If it is in between S1 and P, they have introduced a film, then the shift will be upward. So here minus indicates the shift is downward, or displacement is downward. And remember, this shift is not only for the central bright fringe, it is for all the fringes. Okay, all the bright fringes and also all the dark fringes. Okay, I hope you got it. And this is for the bright fringes. And next we should see the dark fringes, and we should confirm that same shift will be there for the dark fringes also, right? So what is the condition for dark fringe? As I said, that path difference should be equals to odd multiples of the lambda by 2. Okay, so if we equate this, d yn prime by capital D plus mu minus 1 into thickness equals to 2n minus 1 into lambda by small d. You can equate for yn prime here equals to 2n minus 1 into lambda capital D by small d minus mu minus 1 into dt by small d. See, this is the nth dark fringe in case where there was no film. Okay, so yn prime equals to yn minus this shift. Yeah, so what you can notice here, whether the bright fringe or dark fringe, the shift or displacement is same. How much the displacement? Mu minus 1 into capital D small t by small d. Okay, and one more thing I should confirm here itself, because of the introduction of the film. Okay, by introducing the film, the beta will not vary, the fringe width will not vary. Okay, fringe width means the difference of any two consecutive fringe locations. Okay, if you consider n equals to 1, n equals to 2, take the 2 minus 1, you will get the same fringe width as before. Okay, by introducing the thin film in between S1P or S2P, you will not change the fringe width. Okay, and also